Now let's talk about SU3 symmetry, and this SU3 symmetry is it's also called as octet symmetry, or it's also called as eightfold symmetry. Now, it was basically Gell-Mann and Niemann who independently proposed a scheme. What they proposed is that they proposed to classify basically the elementary particles, to classify elementary particles based on the values of y, and what's y is the hypercharge, and we have already discussed it. And this y is b plus s. And this hypercharge and the third component of isospin. Third component of isospin, what we understand as I3. And this combination, I mean, in order to classify the elementary particles based on Y and I3, and this is called as SU3 symmetry, or this may also be called as octet symmetry, or the eightfold way. Now, we understand that mesons and baryons they have similar properties. I mean, mesons and baryons, they have similar properties in a sense, like that all the mesons are bosons with zero spin, and all the baryons are fermions with half integral spin. So we can say that isospin of formalism it was extended to mesons and baryons. I mean, the group of mesons and the group of baryons, and all the particles in these two groups can be regarded as different states of the same entity. And say, for example, I mean, the baryons, what are the baryons here? We have baryons, proton, neutron, chi negative, chi zero, sigma negative, sigma zero, and sigma plus, and lambda zero. These baryons, I mean, the Gell-Mann and Niemann, what they did is that they proposed the existence of a group of these 8 baryons in super multiplet. We call it super multiplet SU3. By plotting a graph, basically a graph between the hypercharge y and the third component of isospin I3, and the value of isospin, its third component, and hypercharge, we would like to illustrate them in a table. That would be the right thing to do here. Is we will have name of the baryon, then we will have the hypercharge, then we will have isospin, then we will have the third component of isospin. So here we have the name of the baryon we'll take here. We will take hypercharge, we'll take its isospin, and then its third component. Now, if we take chi negative, so its hypercharge is -1, its isospin is half, and its third component is -half. Then chi neutral, its hypercharge is -1, its isospin is 1/2, and its third component of isospin is +1/2. And then sigma minus, its hypercharge is 0, and its isospin is 1, and its third component of isospin is -1. and then choosing sigma 0, its hypercharge is 0, and it has it has an isospin of 1, and it has third component of isospin as 0. Then we have sigma plus. It has the hypercharge is 0, and its isospin is 1, and its third component of I3 is plus 1. Then we have lambda, that is, its hypercharge is 0, and its isospin is 0, and its third component of isospin is also 0. Then taking proton, it has a hypercharge of plus 1, its isospin is half, and its third component of isospin is half. And finally, we have the neutron, and it has a hypercharge of 1, its isospin is half, and it has a third component equal to minus half. Now, let's plot. Let's have a graph, what we call as weight diagram. Weight diagram. And so what we have here is we have I3 as x-axis, and we have y hypercharge as y-axis. So what we have here is that the members of the octet super multiplets, they form a symmetric hexagon with one baryon at each corner. So let me go with that. So let me propose this as n, and this is p, and here I have sigma minus, and here I have chi negative, and then here I have chi 0, then here I have sigma plus. And let me try to join them so as to have some idea. These are the particles, and we have a hexagon in action. And now if I take this as dotted line from here to here, let me extend this here, and let me extend this here. Okay, so this is my hypercharge equal to 1, this is my hypercharge equal to 0, and this is my hypercharge equal to minus 1. And what can I say here is the slanting lines that we have here, they basically represent the charges of the baryons. I mean, talking about the charge on P and sigma plus here, charge is Q plus 1. And so the charge on sigma minus and chi negative here, this is Q equal to minus 1. So taking this central slanting line between n, here at the center we have lambda 0, and we have sigma 0. And this slanting line gives us the charge Q equal to 0. Now here I have, this is my plus half, this is my minus half state. So this in all is plus 1, and this in all is minus 1. And here, what I have here, this is my 1 plus 1, and this point is a representative of minus 1. Now, in the similar way, here we have this is the weighted diagram for baryons. In the similar way, we would like to draw the weighted diagram the weighted diagram for mesons. But before drawing that diagram, let's go with the tabular form of this. We have mesons, then we will have their hypercharge, then we will have their isospin, then we will have the third component of their isospin. And so this will represent mesons basically, and this will represent their Y, this will represent their I, this will represent their I3. Okay, now here we have K plus, and K plus, it has a hypercharge of 1, its I is half, its third component is half. Then we have K0, its hypercharge is 1, and its isospin is half, and its I3 component is minus half. Then we have pi plus, its hypercharge is 0, its isospin is 1, and its I3 is plus 1. Then pi 0 gives us 0. It has its hypercharge is 0. Then its I is 1, and its I3 component is 0. Then pi negative, we have 0 hypercharge, we have 1 isospin, we have minus 1 as third component of I3. Then the K0 bar for its hypercharge has to be minus 1, and its I is half, and its I3 is plus half. Then the K minus, for K minus, the hypercharge is minus 1, I is 1 half, and I3 is minus half. And finally, we have eta. For eta, Y is 0, I is 0, and its third component is 0. So let's draw the weighted diagram for mesons. So let's draw this weighted diagram for mesons. So we have x-axis here. Okay, that's definitely I3, and we have y-axis, and that y-axis is a representative of the hypercharge. And we have the particles. So here I have a particle, here I have a particle, here I have a particle, then here I have a particle, then here I have a particle, then here I have a particle, and here I have a particle. Now, so this will give me y equal to 1, this is for y equal to 0, and this is for y equal to minus 1. That's the case. So let me join them. So here I have, this is certainly as per the table, this is K0, this is K plus, and this is pi minus, and this is K minus, and this is K0 bar, and this is pi plus. Now let me join them. They will form an octet like this. All right, that's the case. So here I would like to have an extension, and I would like to have a slanting line here, and I would like to have the extension of the slanting line here. Now here at the center, what we have is eta and pi 0. So this is my plus half, so this is my 1, so plus 1, this is my minus 1, this is minus 1, and this is my plus 1. So here we can see here this Q is simply plus 1. For these particles, Q is simply 0. And for these particles, this Q is minus 1. Now we have what we call as baryonic decuplet. And what is this baryonic decuplet? It was basically predicted by SU3 symmetry. Baryonic decuplet. and and this baryonic decuplet was predicted by SU3 symmetry that we have been talking about. And let's go with the weighted diagram of this baryonic decuplet, or we also call it baryon resonance decuplet. Now, in order to go with this, what we have is we have the third component of isospin, and we have the hypercharge Y. Now, in this case, so what we have is we have particle 1, then let me choose this another, we choose this another, and then here and here, and then here, and then let me put the names of the particles. Okay. All right, now this will represent my y equal to +1 state, and this will represent my y equals to 0. And using this weighted diagram for baryonic decuplet, or what we call it as a baryon resonance decuplet, a new particle was discovered, and that particle is omega -1. So what we have here is delta minus, we have del 0, and here we have del plus, and here we have del plus plus, and here we have sigma 0, here we have sigma plus, and here we have sigma minus, and this is my half, this is my minus half, so this is my +1, and this is my minus. This is my -1. And if you move ahead of it here, you can have 3/2 then, and if you move ahead of this in the negative direction, this will give us -3/2 here. Now here, what I have is chi negative, and here I have chi 0. Now this particle was not here. This omega hyperon at the vertex of this triangle pattern, it was not known at the time of the prediction of this baryonic decuplet, and it was Gelman who gave it the name omega, like this, omega, and predicted and also predicted that it should have, I mean, the predicted properties of this omega minus hyperon are like, I mean, it must have a mass equal to 1680 mega electron volt, and it must have a charge. It must be C squared, and it must have a charge. It must have a charge of -e, and it must have a spin of 3/2 bar, and it must have a lifetime of the order of 10 to the power of -10 seconds. And later on, this omega hyperon, it was discovered, which in fact verified the SU3 symmetry, which was proposed by Gelman and Niemann. Now, what is important here is that this particle, this omega hyperon, was later on discovered. It was discovered in probably 1964, when hydrogen bubble chamber was exposed to K minus mesons of momentum of the order of 5 giga electron volt per C at Brookhaven. And the high energy K negative mesons interact with the protons, and what they do is they produce these omega negative hyperon particles that were predicted using this baryonic decuplet the weighted diagram for this baryonic resonance decuplet. Now, talking about the discovery of this omega hyperon. Now to write down the reaction, so what we have here is K minus and a proton, it gives omega minus and K plus and K minus. And this omega hyperon, what happens here is that this omega hyperon, it decays into chi neutral and pi minus. And this chi neutral, it decays into lambda neutral and pi neutral. And this lambda neutral, it decays into a proton and pi negative. Now, as this lambda neutral, it decays into a proton and pi negative. And what happens here is that this there is a further decay of this pi neutral, it has to be neutral, into the two gamma ray photons. So this pi neutral decays into gamma and gamma. And each gamma ray photon here is converted to electron and positron after interacting with matter. So if I would like to summarize this thing in a very simplest way, we have K negative and we have a proton. What we get here is we get a hyperon omega negative and K plus and K minus. And here we have chi naught and then we have lambda naught, and then what we have is a proton and pi negative. And here this should be chi neutral plus pi negative, and here I will have pi 0, and this pi neutral decays into two gamma ray photons. And these two gamma ray photons, when they interact with the matter, they give the two couples of electron positron electron positron.